Good morning. My daughter is sick this morning, so I'm going to do a quick video on the ideal gas law. So hopefully after this video, you'll feel relatively comfortable doing some practice with that. So I'm actually going to let Crash Course, they do kind of a good intro with ideal gas laws. So I'm going to play that for a couple minutes and then I'm going to go through and actually follow along with some notes for you guys. So let me start with this and then I will pause this about halfway through and we'll continue.
What does your perfect world look like? An end to genocide, corn dogs for dinner every day, David Tennant at my house for board games, and Carl Sagan would be there too. He'd be immortal and not dead. We could cure cancer with puppies and vomit wouldn't exist. Unfortunately, sometimes we need to vomit to survive. David Tennant doesn't know I exist, and while scientists are experimenting with dogs that can diagnose cancer through scent, puppies are not helping to cure the disease. Gases, likewise, don't live in a perfect world either. It'd be great if their particles always fulfilled the assumptions of the ideal gas law and we could use PV equals nRT to get the right answer every time. But the ideal gas law, much like our culture, has really unrealistic expectations when it comes to size and attraction. Namely, it assumes that particles do not have size at all, and that particles never attract each other. Well, I don't know about you, but it's hard for me to take up no space no matter how much I want to disappear, and attraction, so far, that's never gone away. So the ideal gas law often becomes little more than the ideal gas estimate when it comes to what gases do naturally. You remember the ideal gas law? It's a combination of three related laws that were discovered by a variety of scientists. Let's review real quick. Boyle's law was first published by Robert Boyle in 1660, but it was actually discovered by two of his contemporaries, Richard Townley and Henry Power. It says that the product of the pressure and the volume of a gas is always constant as long as the temperature remains the same. Boyle's law requires a closed system where the amount of gas is constant, like in my balloon. Next is Charles' law, which was discovered by Jacques Charles and actually named for him, though it was first published by Joseph Louis Gay-Lussac, who wasn't a scoundrel. Yes, I'm looking at you, Robert Boyle. Charles' law, which also requires a closed system, states that the volume of a gas divided by its temperature gives a constant as long as the pressure is held steady. And then there's Avogadro's law, discovered by resident house elf Amadeo Avogadro, and this one does not require a closed system. In fact, it's all about changing the amount of gas. Like I just did there. It says that the volume of a gas divided by the amount results in a constant as long as the temperature and pressure are held steady. The more gas you have at a given temperature and pressure, the more space it takes up, and vice versa. That's pretty intuitive, right? The trouble is that it's kind of inconvenient to use three different laws to figure out what one sample of gas is doing. So eventually the three laws combined into one by surprise, our old friend Dmitri Mendeleev. He pulled all the elements together into the periodic table, and it turns out he pulled all the gas laws together too. Smart guy. The main thing Mendeleev did was to calculate just one constant, R, also called the universal gas constant, which incorporates the various constants from all of the gas laws. With a little rearranging, we now have the ideal gas law that we know and love. R equals 8.3145 liter kilopascals per Kelvin mole. But don't let the crazy units scare you. It looks complicated, but it's really just a measurement label like meters or newtons, and it helps us out a lot in our calculations.
Just a quick note, I'm not going to have you guys use that value. We're going to use the value when pressure is in atmosphere, and that's going to be on your notes. It's 0.0821. So just keep that in mind. The value that he's going to plug in for R is different than the one that we're going to use, and I'll show you that when we actually get to the notes.
Which is mostly what we'll be doing today. This is all pretty cool, but remember that it's called the ideal gas law for a reason. It only works perfectly when gases behave ideally, with the particles not taking up too much space and not being attracted to each other. It's a bit of an oppressive regime, but under normal conditions, most gases come close enough to ideal behavior that we get very little error. It only breaks down badly in conditions like high pressure or low temperature or high density that shove the particles so close together that they take up a large proportion of the available space. This also causes any attraction between them to be magnified. This is like how I didn't think Alison Kane was that attractive until she became my lab partner, and then she was right there next to me all the time and I couldn't handle it. Johann van der Waals came up with a way to correct the equation for real gas behavior, and we're going to explore that soon. But it's important that we know first how to use the base equation. And besides, it's close enough most of the time without the correction factors, so why make it harder than it needs to be? One last thing, remember that STP, or standard temperature and pressure, is 0 degrees Celsius and 100 kilopascals. But gas law equations are done in kelvins, not degrees Celsius, so we'll call it 273.15 K and 100 kilopascals.
Again, and we're going to use atmosphere and not kilopascal. So STP is 273 Kelvin and 1 ATM. And I just wanted to bring you back to this part a little bit. This is when he talks about the ideal gas law not really working, and he kind of alluded to this. The ideal gas law only works when gases behave ideally, and because we don't live in a perfect world, they rarely behave ideally, but most of the time it's close enough. So it talks about they don't have really much, they don't take up much space, and they don't have a lot of attraction to each other. That's how the ideal gas law works. So if those kind of break down, then the ideal gas law doesn't work. So this is why he's saying that sometimes with the ideal gas law, really high pressure or really low temp or high density, all of those factors cause those gas particles to not only come closer to each other, so they have a higher attraction to each other. Okay, it's also about the space that they're taking up. So those are the three ways in which the ideal gas law does not necessarily work. But again, because this happens rarely, it's for the most part close enough. And that's kind of what we're going to look at today. So I want to go back to the notes. And so I apologize. I don't have a smart notebook on my computer at home. So I'm just going to kind of walk through it with you from your notes. So you can see that the ideal gas law, PV equals nRT, sometimes called PIV-NERT. But with the ideal gas law, you have one of every variable, different than when any of the laws, Boyle's, Charles, Gay-Lussac's, and Avogadro's, all of those deal with an initial and a final, where the ideal gas law, you just have one of each. So these are going to have to also, you're going to have to pay attention to the units that they're in, because there is a value called R, and he talked about this. It's the universal gas constant. And if you notice, the universal gas constant has 4 different values attached to it. It's volume, its pressure, its amount, and its temp. So when you're talking about the ideal gas law, these are the values that all of your other variables have to be in. And if they're not, then that's when this is not going to work. So in Boyle's law, when it was pressure and it was volume could be milliliters or liters. Pressure could be any ATM, mmHg, kPa. It could be a lot of things. But when you're talking about the ideal gas law, your units have to match whatever your R value is in. So we're going to use 0.0821 most of the time. So that means that volume has to be in liters. If it's not, you'll put it there. That pressure has to be in ATM. If it's not, you'll put it there. That amount has to be in moles. If it's not, you'll put it there. And temperature has to be in Kelvin. And if it's not, you'll put it there. So lots of converting with the ideal gas law because it has to be in those specific units. And it's also kind of important to note that if you are reading a gas laws problem, it's not going to give you your R value in the problem. You're just going to have to know that your R value is going to go into that equation. So if you look at the example over here, it says a sample of oxygen gas is confined in a 10-liter container at 680 millimeters of mercury and 32 degrees Celsius. How many moles of gas are in the sample? So it looks similar to combined because you have a lot of those variables together. However, the combined does not involve moles. Okay, it's only pressure, volume, and temp. So that's also kind of a note that you have the ideal gas law, and it also gives you one of everything. Whereas with the combined, you had 2 pressures and 2 volumes and 2 temps, and you kind of had to weed through what you had there. You're just going to be given one of each. So in this case, again, you're just going to pick out what your variables are, and then you're going to plug them into your equation. So for volume is 10 liters. That's acceptable. That's what my volume needs to be in. So that's okay. My pressure is 680 millimeters of mercury. That is not acceptable because my pressure has to be an ATM. So I'm going to do a quick pressure conversion, divide by 760 to get 0.895 ATM. Temperature is 32 degrees Celsius. Again, we're going to make that into Kelvin. And then the R value, again, that's not given to you in this problem. So just pay attention to that. You're going to have to plug that in. So PV equals nRT. So 0.895 times 10 equals N, which is the amount in moles, times your R value, which it didn't give you, but you're going to have to plug in, and then times your temp. So when you solve for all of that, you get 0.36 moles. And again, because R involves moles, then when you solve for N, it's automatically going to be in moles. If this were to have asked how many grams, you would have to solve for moles first, and then you would have to convert to grams. So let's go down here and do an example together, and then I'm going to let you guys try this one on your own. So it says if you have 108 milliliters of butane, which is C4H10, at 715 millimeters of mercury and 25 degrees Celsius, what is the mass in grams of butane? So again, this is talking about what I just mentioned, in that you are going to solve, anytime it's asking for mass, you're going to have to solve for moles, and then you're going to have to convert that into grams. So let's kind of look at the variables we have here. 108 milliliters is our volume. And I'm going to have to convert that into liters. So divide by 1,000 or move your decimal 3 spots to the left. So I have 0.108 liters. I have 715 millimeters of mercury. If you divide that by 760, you're going to get 0.94 ATM. And then add 273 to 25 and you get 298 Kelvin. And then I'm going to use 0.0821 as my R value. And I have over here just a quick, I just typed it out for you really quickly. So here's my variables. I have volume, I have pressure, I have temperature, and this is what it looks like plugged in. So 0.94 times 0.108, and then I'm going to divide that by the product of 0.0821 and 298. So when I solve for all of that, I get 0.00415. And because that is N, that's automatically in moles. But the problem itself asked us what's the mass in grams? So I'm going to take this moles and I'm going to convert it to grams. And you do that just by multiplying by its molar mass. So if you look, butane is C4H10. So essentially 48, 12 times 4 is 48, plus 10 is 58. So that's why I multiplied by 58 grams, because that's the mass of butane. And I'm going to get 0.24 grams of butane. So that's a good example of, there's a lot of conversions in there. So again, this gas law is not necessarily difficult. You just have to pay attention to how your values are given to you, because unlike other gas laws, they do have to be in certain units in order for you to plug them in. Okay, so I'm going to let you guys try one here. So a steel tank has a volume of 438 liters and is filled with 0.885 kilograms of O2. Calculate the pressure of O2 at 21 degrees Celsius. So I'm going to have you guys pause the video and try this in 1 second. I'm going to give you a hint though. Anytime you're given mass, it's talking about N, and because N has to be in moles, this is where you would have to convert yourself from kilograms to grams, and then grams to moles, and then you can use that value for N. So go ahead and plug that in, and I want you to pause the video and solve for it, and then press play again, and I'll go through the answer and see if you got it right. Okay, so at this point, you should have paused it. You should have already completed the problem. So now let's walk through the answer and see how you did. So if you go down here towards the bottom, so I have 0.885 kilograms. So I know that I have to convert that to grams. So divide by 1,000, it's 885 grams. O2 has a molar mass of 32 grams. So if I'm going to go from grams to moles, I'm going to have to divide by the molar mass. So divided by 32. So here's my number of moles. So all that work just to get my N value. My volume was 438 liters. I didn't have to convert anything with that, so that one was okay. My temperature, 21 degrees Celsius. I'm going to add 273, and that's where 294 came from. And then again, my R value, which wasn't given to me, but I know that it's the ideal gas law, and that's where that's involved. So I'm solving for pressure. So again, I'm just going to multiply these together, and I'm going to divide by 438. And if you do that, you should have gotten 1.5 ATM, which that's a pretty valid atmospheric pressure. So if you were to get something like 800 ATM or something crazy like that, that's something that you would probably want to adjust and pay attention to, because ATM, you're not going to have crazy high numbers like you would with millimeters of mercury, just because of how the unit itself works out. So that would be something also to kind of pay attention to. But 1.5 sounds like a reasonable number. And you could always double check your work, because if you plug it back in here, actually they should equal each other. So if you ever were a little unsure, plug it back in and then multiply and divide and see if all of those are equal to each other. And then you can double check if you did that right or not. Okay. So ideal gas law, again, not terribly difficult, but it can be kind of a pain just by having to convert all your units. So if you will just triple check that your units all match liter, ATM, mole, and Kelvin. And I wanted to show you, I didn't let the video play this far, but he does talk about, he does an example problem on here. And again, he uses kPa for his R value, so kind of ignore that. But whatever you're solving for, all of these units end up canceling. So like moles is going to cancel. So this one he was solving for volume. So moles would cancel. Kelvin's going to cancel. kPa, or you're going to have ATM, is going to cancel. So again, it's just trying to show you that all of those units that are there, that's why you only end up with one when you're done, is because based on that R value, because it carries all four of those units, eventually all of those will cancel out and you'll be left with whatever one you're solving for. So in this case, he was solving for volume, and liters is the only one that doesn't cancel out, which makes sense because that's what he was solving for. So again, that's why that R value does carry all of those units. It's a constant. It helps with the accuracy of the ideal gas law, because he did talk about it's not, gases don't act ideal. It'd be great if they did, but they don't. So this is close enough, but this kind of helps kind of keep it all together and keep it as accurate as possible. Okay. So if you guys will now then work on the practice that the sub is going to have for you. And then I am hoping that I am back tomorrow, and then we will continue this. We're going to do a lab with the ideal gas law in just a couple days. So if you have any questions, either message me or write them down, and I will address them when I come back. All right, guys. Thanks so much. Bye.